It's a pleasure to welcome Mark Owen today. Mark did his PhD in Manchester on the D0 experiment on Higgs 2 tau tau in 2008, and then moved to Atlas, where he started working on the trigger and the TT bar cross-section. In 2014, he changed to Glasgow, where he became a professor 2 years ago. And in Glasgow, he works on TTH, the HLT, and also was for a while the top group convener. So we are looking forward to hear more about the top today, and the floor is yours.
Yeah, thanks very much for a nice introduction. It's always great to come to CERN. So it's my pleasure today to talk to you about a new measurement of the top quark mass with Atlas. And we've done it with what I'm going to call boosted tops, and that means tops with high transverse momentum. Okay, so outline of what we're going to talk about in the next about 40 minutes or so. So try and introduce why we want to measure the top quark mass. Why is this interesting? And why do we want to use these boosted top quarks? After that, we're going to see that jets are going to be an important aspect of this measurement. We'll see that at the end. So I'm going to spend a little bit of time, I should use a pointer, not my hands, talking about jets in Atlas. And then I'll start on the actual measurement, go through how we set up the analysis, and then show you the fits of the data and get to the results. And at the end, I'll have a little bit of an outlook towards the future and the high LUMI LHC. Okay, so why do we want to measure the top quark mass? So in the standard model, we generate all of the fermion masses with Yukawa interactions with the Higgs. So the mass of each quark just comes with the equation you see on the slide here. So this is for the top. It's just related to its Yukawa coupling, which is called Y here, the vacuum expectation V, and then there's a factor of square root 2. So in the standard model, neither the Yukawa coupling or the top mass, they're kind of interchangeable, are predicted, so we've got to measure them experimentally. And I'm an experimentalist, so of course it's, you want to try and measure these things. But the top is kind of really unique here, because we know its mass is about 170 odd GeV. And so if you look at the value of the VeV here, which is about 250, then you see that this Yukawa coupling is order 1. So this means the top is interacting strongly with the Higgs boson, and that's kind of unique among the fermions. So all the other fermions are much lighter, B quarks, charged leptons, and neutrinos, and so on, all much lighter. So this is the only guy that's really interacting strongly with the Higgs. And that means it plays a big role in understanding if the whole standard model is consistent. And that's because it enters in loop corrections. So this kind of diagram I've got on the bottom here, where we've got a top going around the loop, is like a correction to the Higgs mass. And so when we put all of our measurements together across all of the electroweak sector, we can essentially test if the standard model is really self-consistent. So we can see if the measured values of all the masses are lining up, even though if they're not predicted. The fact that these loop corrections are there means they all get linked together. And another way of looking at that is to say that we're actually probing for new physics, because of course if this test fails, so if we find that the masses are structured in such a way that they don't agree with the loop predictions of the standard model, that would perhaps imply that there's some other particle going around this loop, some X or something that we don't know about, and so that would be some evidence of some new physics entering into these loop corrections. So we want to try to measure these masses, the most important being the top quark mass, which I'll talk about today, W boson mass and Higgs boson mass, as precisely as we can. Okay, so this is sort of how that looks in pictures. So this is one of the electroweak fits, so there's a few out there. I've just picked one recent one from a couple of years ago. So on this plot, I just want you to look at the blue ellipse. So this shows you the value of the top mass on the y-axis and the W boson mass on the x-axis that is consistent with all of the other electroweak data. So that's the blue ellipse. And then what we want to do is measure those two masses directly in the experiments, and they give you the gray shaded lines, and see if everything lines up. Now, as people are probably aware, there's been a bit of a controversy with the W mass recently. So this particular electroweak fit, you see it's kind of off to the right a bit. I'm sorry, this line here is off to the right compared to the electroweak fit. That's because this has the CDF and W mass measurement, which was rather high. The recent CMS measurement would actually be in rather better agreement with the precision data. So the red lines are here my attempt to sketch on that very nice, precise recent result. I didn't manage to find a fit that actually contained it yet. So hopefully that's coming soon. Okay, so today we're interested in the top quark mass. And of course, you see here the position of that on the y-axis is important in seeing if this thing all hangs together or not. Okay, so where do we stand with the top quark mass? So first to show you where we got to in run 1. So actually last year we completed the combination of all of the Atlas and CMS run 1 top mass measurements. These are all the direct measurements, so the blue ones on top are Atlas, red ones in the middle are CMS, and then the final combination is right at the bottom. We also do some cross-checks in the individual channels. And what's nice here, because we're working within the experiments, we can do a proper treatment of all of the correlations and do a proper statistical test to see if the data is all in agreement with a single top mass, which it is, so we have really good agreement here, 7.5 chi-squared for 15 degrees of freedom. And the final precision here is 0.33 GeV, so rather precise. So that's, I think, a very nice achievement from run 1 LHC, but that's not the only place we have precision measurements of the top quark mass. So we also have the tevatron combination. So that's the point in pink sitting on the top here. This is the run 1 LHC value, the black point. And now we start to have results from the 13 TeV run 2 data. It does take us time to do these precision analyses. And one particularly interesting one here from CMS, which has a rather good precision. So that's actually the single most precise result done to date at 0.37 GeV. And you see here there's maybe some signs of a little bit more scatter between the different data measurements. What we're going to try to do here today is add a new point to this plot with hopefully good precision and see if we can enlighten a bit more on the situation. Okay, so we want to measure the top quark mass. So at the LHC, the best source of top quarks is TT bar production. So there's the leading order diagram, just gluon fusion. And you probably all remember that the top quark is decaying in the standard model into a W boson and a B. W then goes into either lepton neutrino or pairs of quarks. And in this analysis, we're going to be looking at the case where one W goes leptonically and the other one hadronically. And that gives us this lepton plus jets final state here, so with either electrons or muons. And it's quite a nice balance between a reasonable branching ratio, so you see 15% for each lepton flavor, and having a nice object to trigger on and very small backgrounds. That's how we produce the tops. Now, why do we want to look at tops that have got high momentum? So here's our Feynman diagram for our lepton plus jets final state. So normally what we expect is each of these quarks in the final state here, so we've got 2 light quarks and 2 B quarks, are going to produce a jet in our detector. And so if the tops are at low PT, this is a kind of sketch of the sort of thing we expect to see. We've got 4 jets, we've got a lepton somewhere, and they're all kind of separated from each other. Now, our detectors are very good at telling apart B quarks from light quark and gluon jets, so I've shaded those guys a different color, so that indicates we can reconstruct them. However, we still have a combinatoric problem here, because we want to measure the top mass. So, for example, we want to try and reconstruct the decay products of the individual tops, so we can look at their invariant mass. So we need to resolve which of the 2 B jets you see in the picture is paired with the lepton and which is paired with the W. So that's kind of not completely trivial. And this is where the boost helps us. So in the middle picture here now, I've added to the cartoon a boost in the transverse momentum for both top quarks essentially, but for the hadronic top quark is the one we're most interested in. And you can immediately see here how now the B jet here that's come from the hadronic top is nearby to the 2 jets from the W boson. So you kind of have just a topological way of seeing which B jet is associated with which top. Now, when we do the reconstruction in the electrical analysis, what we do is we start with the standard jets in Atlas, so they are anti-KT with radius of 0.4, and then we use those as input to a second stage of jet finding where we use a large radius of 1.0, again anti-KT, and we call these reclustered jets, as that's indicated by the green cone here. And so the idea is that's containing then hopefully all of the decay products of the top quark. A nice thing with this technique, so here I've got the case where we've seen 3 separate jets in the detector from the 3 quarks. But of course, as the boost goes higher, you expect these jets are going to start to merge together, and that's kind of seamlessly done when you do jet reclustering. So you also have the case where there's just 2 jets inside your top quark without doing any kind of special treatment. That's just picked up by the jet reclustering. Okay, so that's the picture. Now you might say, oh, well, this combinatorics problem is not very big. You've only got basically two choices of which way to pair the B-jets. But you shouldn't forget that at the LHC, we have a lot of the time extra QCD radiation. So this kind of thing where there's a gluon produced, for example, in the initial state, happens more than half the time, essentially, if you look at TT bar events. And of course, these guys are rather difficult to distinguish from the jets from the W. And so now your resolved channel, so your low PT channel, which I've lost the pointer, is on the left here. So this blue jet would be the one coming from a gluon. So now you've got an additional combinatoric problem to solve here. And again, in the sketch, you kind of see how the idea is the boosted channel helps you with that because the decay products at the top go collimated together. Okay, so that's the idea. We want to use this large radius jet that we've found here and use it to measure the top quark mass. Now, if we're going to do that, we can kind of immediately guess we're going to be depending on how precisely we can understand these jets here, because the energy scale of these is going to directly affect the mass extraction of the top. That's why I'm now going to spend a few minutes talking about how we do jet reconstruction at ATLAS. Okay, so lots of ways of looking at the ATLAS detector. I kind of quite like this one. So it's a picture of different types of particles going through our different detector subsystems. And one of the beautiful things with TT bar events is that you get a real sort of see every type of particle. So we've got muons, we've got electrons, we've got jets, which give us neutral and charged hadrons, and we've also got neutrinos that pass through the whole detector. And in particular for the jets these days, we exploit the particle flow algorithm. So that's the idea that charged hadrons we can measure often better with our inner detector than with our calorimeter. And so we're going to try to exploit that when we build the jets. Now, the analysis I'm presenting today is using the LHC Run2 data. So that's a beautiful data set collected in 2015 to 2018. And you see here the sketch of how the luminosity evolved over the years. And now very well understood within the collaborations. And so also a nice chance to say thank you to everyone who operates the full accelerator complex that makes all this happen. And hopefully we have another good year of data taking this year. Okay, so I mentioned that we want to use our tracker as well as our calorimeter for our jet reconstruction. So that's the idea of particle flow. So exploit the higher resolution of the tracker at low transverse momentum. And so this is a sketch of how the particle flow algorithm works. So the gray blocks here, these are clusters reconstructed in our calorimeter, and they're colored. So the red ones is where there's some energy associated with the tracks of charged particles. Green ones are neutral. And hopefully you can see, at least you can see it on the right-hand plot, the purple points. So these are tracks that are associated with the jets. And so the idea of the particle flow algorithm is wherever there's a track, we subtract off the expected energy in the calorimeter. So as we go from left to right, that's the subtraction happening. So you see, for example, this block here, which I'm struggling to circle, is subtracted away on the right-hand side. And then the algorithm runs on the inputs to the jet algorithm are then the particle flow objects, which are essentially some of the tracks and the remaining energy in the calorimeter. So this is kind of the perfect picture. So this is a simulation with pileup of 0. And of course, we don't use very much data that has pileup of 0 in an analysis like this. So we have more like pileup like that. No, now I've missed a slide. Okay, more like this guy. So this is a simulation with 40 interactions overlaid. So now see much more messy, lots of energy in our calorimeter and lots of extra tracks. But with this, we can see one of the additional benefits of the particle flow technique. So if you look on the left-hand side here, so the way the algorithm works is we take all of the tracks and for each track subtract off the energy we expect in the calorimeter. So the blue now is, the blue is energy that's come from pileup. If you look over here, you see there's some pileup energy, and there's also one of these yellow tracks. So this is a track that's not associated with the main primary vertex. So we subtract off that energy because it was associated with that track. And then when we run the jet finding, that track is not included because it's not on the primary vertex. And so that way we make our jet algorithm much less susceptible to pileup than it would be if we were using the full calorimeter information. So the impact of that is shown in this plot here. So the first plot on the left shows you the rate of jets coming from pileup. They're called fake jets here. And the blue line shows you what we would have if we were just using calorimeter, jets only using a calorimeter. So we get quite a high rate of pileup jets. The green line is the particle flow algorithm, so you see orders of magnitude better. Now, of course, we did always have the ability to use the tracking, and so the red line would have been what we would have got in like a run-1 style analysis, where we use the tracking information to reject this, but you see we don't do as good as the particle flow algorithm, and it actually costs us some efficiency. So the other plot shows you the efficiency of the jet reconstruction, and you see the particle flow algorithm in green staying very close to run 1 across the whole PT spectrum. Okay, so we have this nice jet reconstruction. Now, what matters for the top mass analysis is the ability to understand the energy scale of these jets. So I'm now going to spend a few minutes talking about our jet energy scale calibration at Atlas. So this is a series of corrections that are applied, and the first 5 here are all done with the simulation, and then the last one brings the data and the simulation into agreement. We start off with the reconstructed jets, which I've just talked you through. We then make 2 corrections for pileup in the first red box, and I'll talk through those in a minute. We then correct the jets back to the hadronic energy scale. Then we have a global sequential calibration that just improves the resolution and reduces a little bit the flavor dependence. And then finally, the in situ calibration in the data. I don't have time to go through all of them, but I'm going to talk a little bit about the pileup corrections and then about the in situ calibration, because these are the things that come through at the end into the final measurement. So starting with our pileup correction, so this is the formula we use. So the PT here on the right-hand side, so that's the uncorrected PT, so the PT after the jet reconstruction. And we need to subtract off contributions that are coming from pileup. So you remember in the picture before, we had still quite a lot of energy from the pileup. So the first term here with the red row, so this is what we call the area correction. So the idea here is you look event by event at how much energy there is in the detector and subtract that off from all of the jets. So in this plot, you see why you want to do this event by event, because event by event, even for the same number of interactions, so this mu is telling you how many interactions here, so you see we've got about 37, 38 here, there's quite some variation in how much energy is deposited into the detector, and so this is the estimated row using the algorithm, and you see it's varying from like 5 to 25 GeV. And it, of course, strongly depends on how many vertices, so the NPV here is how many vertices we've reconstructed in the inner detector. So this is not a small correction. You see the scale here is tens of GeV, and we're going to try to measure the top mass to better than 1 GeV by the end. And so the uncertainties on this we're going to see come through in the measurement at the end. So that does kind of most of the work of removing the pileup from the jets. So the second plot shows you how the transverse momentum depends on how many vertices we see in the detector. So you want that this derivative is 0. That means you're independent of the number of vertices. So before the correction, of course, you have a positive effect everywhere in the blue. Now you make the area-based density correction. You go to the pink points, and that does quite a good job of removing most of the effect, but you see kind of higher pseudo-rapidities. There's still some pileup dependence here. And so then we have the last 2 terms that remove the residual pileup dependence. But again, this is using the simulation, so we're going to have some uncertainties on this. They're going to turn up in the end of the measurement. Okay, so now we've used the simulation. We've corrected our jets for pileup. We've also done the correction to get them to the hadronic energy scale. Of course, we don't expect that our data exactly matches our simulation, so we need to correct them to bring them to the same scale. And the basic principle here is to use the conservation of transverse momentum. So essentially, you're trying to calibrate one jet that you're not sure of the energy scale of to some other object that you've already well calibrated. It's a 3-step procedure in Atlas. So first, we do what's called the ITER intercalibration. So we start with central jets, and then we make sure we bring the scale of all of the other jets in the forward region, where forward means this region, to match the scale of the central jets. So it's like a relative calibration only. To set the scale of the central jets, we use Z and photon plus jet events, where the Z is decaying into leptons. So in both cases, you've got well-calibrated objects you can use to do the transverse momentum balance. And then finally, we have multi-jet events that allow us to calibrate very high transverse momentum jets where they're recoiling against a system of low PT jets, which have already been calibrated by the previous steps. So don't have details. These are like full physics analyses essentially to do these. So I'm just going to show you one nice event display of the kind of event that's helping with these calibrations. So this is a photon plus jet event from 2015. And you see very nicely here on the left-hand side, energy in our EM calorimeter in yellow. So that's the photon. There's no track here. So it's a photon. And then on the right-hand side, energy deposited in both calorimeter systems and also a bunch of tracks pointing at that energy. So this is the jet. And you see they're very nicely back-to-back in phi, so balancing each other. So by measuring the ratio of the jet, essentially, it's not quite like that, but the ratio of the jet momentum to the photon momentum in both data and simulation, and doing the double ratio, you then can correct so that the data and simulation are in agreement. So the final in situ jet energy scale is a combination of all of those different methods. And this first plot here shows you the relative weight, so the importance essentially of the different methods. Now we're here interested in jets going from about 30 to a couple of hundred GeV. So you see in this regime, we're dominated by the Z plus jets with the contribution from the photon plus jet events. Doing each of these analyses is like doing a full physics analysis. You have to address all the systematic uncertainties. And then we propagate the systematic uncertainties through the in situ analyses, through the combination, and we get a set of uncertainties that we're then going to apply in the measurement. And we do an eigenvector decomposition of these uncertainties, of which there's a rather large number, to get to a kind of manageable number, which capture all the important dependencies, and in particular, things like the PT and eta dependencies in the uncertainties. So in the final measurement today, there'll be 35, I did my math right, yep, 35 components for the jet energy scale, 25 of which come from the in situ measurements here, 4 from the pilot corrections that I talked about a few slides ago, and then 6 for the flavor uncertainties, which I'll talk about on the next slide. After all this work, where have we got to? So that's summarized in this plot here, which is for central jets as a function of PT. So this shows you the jet energy scale uncertainty. So you see we're down to a couple of percent here in the regime we're interested in. However, if you look at the plot, you'll see that the in situ calibration, so that's the red line, is not dominating anymore here. So it's actually rather small compared to the total in the black line. The two most important effects are this probably quite hard to see kind of gray-brown line. That's the uncertainty from the pileup. And then this green line, which is the flavor response uncertainty. And I'm going to spend a minute or two talking about that now. What is this flavor response uncertainty? So this accounts for the fact that there's an uncertainty in the difference in the jet energy response for jets that originate from quarks and gluons. And our calibration samples are mainly dominated by quarks. So in this plot here, so this is kind of the status in like 2020, 2021 or so. The way we address this uncertainty is we did a relatively coarse comparison by just comparing Pythia and Herwig for the gluon jet response. And then every jet in a physics analysis sample was scaled, had that uncertainty applied, scaled with the fraction of gluon jets in the sample. There's always a separate uncertainty for the B jets as well, so that was always the case. So that gives the green line. There was also an additional uncertainty, which is the blue line, which was small here, but was not actually always small in top mass analyses, which is a flavor composition uncertainty, which essentially is a composition of how many gluons versus quarks there are in the sample, which was actually potentially double counting with some of the modeling uncertainties on the TT bar side. So this, there was an effort to improve the treatment here, which is documented in the paper at the bottom here and this pub note. So what's happened now is that instead of doing one single comparison between Pythia and Herwig, we've tried to split it up into the underlying physics differences. So we changed, so each time we're trying to change just one aspect of the simulation. So the first component is changing the shower with the same hadronization. Second one, changing the hadronization model, keeping the shower the same. And then finally switching between an angular ordered and dipole parton shower, but again, keeping the hadronization model the same. So that's the first set of changes. The second set of changes is that we do a kind of slightly more precise treatment inside the simulation. So instead of applying the uncertainty to every jet apart from the B jets, we now look jet by jet at the flavor in the simulation. Gluon-initiated jets get an uncertainty that's the difference. So this delta is the difference, or the uncertainty in the difference in the response between quarks and gluons, of which there's going to be 3 components. They get the plus sign, and the light quark jets get a minus sign. So that means the response of the two is moving apart in a correlated way for each of these changes. And then we still keep an uncertainty for the heavy flavor jets, so for C and B, but again, it's now also broken into these three components. So there's going to be three of these delta HFs showing up in the measurement. The final detail here is that we scale these response differences with the fraction of quark jets in the Z plus jet selection. And so that this means that we get a zero flavor uncertainty if we do a physics analysis with exactly the same sample we did the in situ calibration. And that makes sense because the in situ calibration was done in the data, so we know we have the correct scale there. Okay, so that set of work led to quite a substantial improvement in the precision of the flavor uncertainties. So now on this slide, so the green here is the old total jet energy scale uncertainty that I showed a couple of slides ago, and the black is the new one. This is showing it now for quark jets. So you see a substantial reduction here in exactly the kind of energy regime we care about for the top mass analysis, which is around here. And so now the flavor uncertainties are these three lines down here, the blue, the green, and the pink. So you see they're rather small. And now we're dominated by the pileup and the in situ jets at higher PT. There's substantial improvement in the precision here, which helps directly in this measurement. Okay, so I spent some time on the jets, but I think it's worth doing that because these come through in the end when we see the final result. So now I get to spend some time talking about the actual measurement. Okay, so here's a cartoon of our events. So we've got our TT bar events. We've got a lepton, so we're going to require one high PT lepton. We're going to require two B jets. And one of these is going to be near the lepton, that's kind of sketched here. And one of them is going to be inside our large radius reclustered jet. And this jet has got to have more than 355 GeV. So that's the kind of regime where you're boosted with high momentum. Inside this jet, there must be at least two subjets, and one of these is the B-tag jet that I just mentioned. And then the invariant mass of this jet is somewhere near the top mass, so we have a window of around 100 GeV, so fairly loose. And that's enough to give us a very clean sample of TT bar events. A couple of extra selection criteria on the missing transverse momentum, MTW, and the invariant mass of the lepton B that just reduce the backgrounds a little bit, but that's not particularly important. Now, everywhere in a few slides, I'm going to be showing you plots where we have simulated TT bar events. So all of our baseline simulation is next to leading order Powhig plus Pithier 8. Okay, so it's always nice to see how these events look in the detector. So here's one of the selected events in the data. So on the top part of here, so you see here 3 reconstructed jets. So in the analysis, these get reclustered into one large radius jet. The blue one is the B jet. And so this we infer coming from the hadronic top, so going with very high transverse momentum, nearly 500 GeV. And then in the lower part, we see what we think are the decay products of the leptonic top. So the blue line is a reconstructed muon, so you see nice hits, if I can get the pointer to go over there, in the muon chambers, in the end cap here. And then one more B jet, so that's the blue jet, and you see also here another jet that's not B tagged. And as I said earlier, lots of these events do have additional jets. And this one is noticeably close to where you can imagine the top leptonic top vector is pointing somewhere in this direction. And that's going to be important in a few slides. Okay, so very nice looking events. So the top mass we can get by just looking at the invariant mass of this large radius jet that we've reconstructed. And we get this nice peak here. So you see centered around 170 something GeV. And here you immediately can see we're sensitive to top mass. So the black line is a simulation with a top mass of 172.5. The blue is 171, and the red is 174. And obviously, as you change the mass, the peak position is shifting. So lots of different ways you could use this distribution to actually do the extraction. We're going to do a relatively simple thing, which is to just take the mean of this distribution. So this MJ bar now is the mean of this jet mass distribution here. And this mean is found to be just linearly depending on the top mass. So the x-axis on the second plot is the input top mass in the simulation, and the y-axis is the reconstructed mean. And you see a very nice linear dependence, which means we relatively simple when we want to set up the fits. We don't have to do here guess a shape for this distribution, which is rather difficult to do. Now, we can already from this kind of figure out whether we're going to be systematics limited. So we have about 65,000 TT bar events expected. If you look at this resolution and do a quick little bit of maths on Gaussian, you'll find we're looking at a statistical precision of 100 to 200 MeV here. So we're going to be dominated by the systematic uncertainties, so I'm going to need to spend some time telling you about those. So sorry, this is a kind of a slightly dry slide, but I think we kind of have to go through it. So these are the list of the most important systematic uncertainties. So fortunately, I spent about 20 minutes discussing our jet energy scale, so that's going to be important. So we have these 35 variations that I've already discussed. Next thing is the jet energy resolution. So this is also measured in the data using very similar kind of events to the jet energy scale. And in a similar way, we do an eigenvector decomposition of the uncertainties. So that gives us 13 variations of the jet energy resolution propagated to the measurement. Then after that, the next important set of uncertainties are coming from the modeling of the TT bar events, because we're going to use the simulation to give us the mapping between what we see in the detector and the top quark mass itself. So here we have 12 variations plus the PDF uncertainties, which are 30, but that's not like 30 separate uncertainties. It's really like 13 different kind of variations. And I tried to split them up here according to roughly the kind of physics that they're addressing. So where possible, we're trying to change only one thing in the simulation at a time to give plenty of freedom when we do the fit in the end. So the first set here are addressing the fact we have a next to leading order calculation, which of course is not infinite precision. So we vary the scales in that calculation. We also do a reweighting of the sample to match next to leading order, because it's actually known that the PT distribution of the top is outside of the scale uncertainties. And then we have the PDF uncertainties from PDF LHC. So then still perturbative QCD, we have the shower. So we make various changes inside the shower, change the scale of ISR and FSR, and some changes in parameters that affect the kind of matching between the shower and the matrix element calculation. So these H-stamp and PT hard parameters. And then finally, we make a change of the recoil model for emissions from the B quark in the top decay, and I'll say a little bit more about that in the next slides. And then we have some uncertainties that are a bit more on the non-perturbative side, although not completely, because we also changed the shower here. So the first one of these, we're switching from Pythia to Herwig, so that's changing both the shower and the hadronization model. We have an alternate underlying event tune and two different models for color reconnection. And so all of these get propagated through the analysis. Okay, so now let's do the simplest thing. So we're going to look at what uncertainty we would expect to get if we just fit only the mean of the invariant mass of our reconstructed top jet. We're going to do this with a profile likelihood fit. So this mean is distributed like a Gaussian, and it's going to depend on the nuisance parameters, which I'm always going to call theta. And the nuisance parameters get the kind of standard Gaussian constraint terms, which are the last term on the right-hand side. So this is the data before we do any fitting in black compared to the TT bar simulation in white. And you see there's non-negligible uncertainty here. Some of this is normalization effects, which won't really affect the measurement, but there's also substantial uncertainties from the modeling and the jet energy scale. So if you do the measurement like this, you would get something like 1.66 GeV, of which the jet energy scale is completely dominating. So of course we want to try and do rather better than that. So now the idea is we want to add some additional observables into the fit so that we can use the power of the data. We've got 65,000 events here to reduce the impact of the systematics on the measurement. So the first thing we do is something that's been done in many top mass measurements. So we exploit the fact that we have a W boson decay inside our top jet. And of course, the W boson mass is very well known. So if we can reconstruct the W boson, it will be sensitive to the jet energy scale, because there's two jets here, but not to the top quark mass. So we can use it to control the jet energy scale. So we look at the subset of events where we've got at least 3 subjects in our top. So that means we can pick out 2 that are going to be from the W. And we see that this reconstructed mass nicely peaks here around the W boson mass, so just a bit above 80 GeV. And the red and the blue line here show you what happens when we change one of our jet energy uncertainty. So this is one of the 35 nuisance parameters, one of the larger ones. And you see quite a substantial change in distribution. The peak is moving as you would expect. So we can include that in the fit by adding Poisson terms for each bin, where the number of expected events depends on the nuisance parameters theta. This mu here is just for the TT bar cross-section, so that we don't have a dependence on the assumed theory TT bar cross-section. And so this then adds information and reduces the impact of the jet energy scale. So that now goes down to 0.30 GeV, and our total precision, in this case, the expected precision would be 0.63 GeV, so very big improvement. And now if you look at what's making up this 0.57, so I already said we have the jet energy scale, but this recoil model, which I alluded to slightly earlier, is actually coming up as a rather large 0.36, so we wanted to have a look to see if we could reduce that further. So before I explain how we did that, I'll try to explain a little bit what this uncertainty is and why it matters here. So there is essentially, when you have the parton shower, there's an ambiguity in which particle or system you use to absorb the recoil when you emit a gluon. This only starts at the second gluon. The diagrams here have only often got one gluon, but in the Monte Carlo it is only at the second because of the matrix element corrections. So what this does in practice is it changes the amount of wide-angle radiation from the B quark. So I've tried to sketch that for you here. So imagine this kind of gluon here that's come off this B. If this is at wide angle, then some of this energy is going to make hadrons, is going to go outside of the jet cones. And that means the invariant mass of this jet would go down when I change the model for the same top mass. So it's a direct systematic uncertainty on my mass measurement. So that kind of would happen in any top quark mass measurement that's using the Bs. But there's a second effect in the boosted, which is also important, is that also these wide-angle radiations can go from the B to the light quark. And of course, we're using the invariant mass of these two jets to try to control our jet energy scale. And this has a kind of slightly nasty effect that this kind of radiation increases the invariant mass of this pair, while the same effect is decreasing the invariant mass of the top jet. And that's like the opposite to what should happen for a jet energy scale, and so effect where everything goes up when you increase the jet energy scale. And so that's why the combination of these two effects is why this is coming up at 0.36 on the previous slide. So what we try to exploit here is the fact that we've got, of course, two tops, one top, one anti-top. And so on the other side of the event, we've also got a B-jet. So if there's more wide-angle radiation happening here, it must also happen here. And then some fraction of the time, we can actually reconstruct this guy as a separate jet from the B-jet. So this blue cone now is indicating that we found another jet. And the idea we had is that if we reconstruct the invariant mass of all four of these objects, then when we get more wide-angle radiation, we should get more events where the invariant mass of these guys is near the top quark mass, so around 170 GeV. And essentially that works. So this plot shows you here the invariant mass, which we're going to call MTJ, so it's kind of invisible here. So that's the invariant mass of these four objects. And the black line here is the nominal simulation. The red line is where we change this recoil model. So if you look at large invariant masses, there's essentially no difference. So when you're away from the top quark, you're just looking at general QCD radiation in the events, so changing the recoil model doesn't make any difference. But then near where the top quark is expected to be, so this is around 170, you see there's quite a substantial difference between the models. And so this we can put in the fit and allow the data to tell us which model is preferred. That's what we did, and that gives us the final likelihood for the fit. So we've already met most of the terms here. So we had our Gaussian constraint terms, the term for the mean of the jet mass, so that's where the sensitivity of top mass is encoded. We've got our invariant mass of essentially the W boson that's going to help with systematics, and now our MTJ, which is the invariant mass on the leptonic side, including this extra jet, which again is sensitive to the nuisance parameters, but not the top mass. Now we can look at the expected uncertainty we have with this setup, and it improves again. So now we're down to an uncertainty of 0.51 GeV. And if we look at the breakdown of the systematics, so the total systematics here, 0.44, they're actually kind of spread out across a combination of the jet energy scale uncertainties and also then different aspects of the TT bar modeling. So you see appearing here, color reconnection, ISR, FSR, and so on. And the recoil now, because we've added this additional observable, is a much milder effect, just below 0.1 GeV. Okay, so this setup that's going to give us quite nice precision. So now we want to convince ourselves that the setup is actually going to work when we apply it to the data. So the first thing to do is, of course, check that if you put a top mass that's different from the one in your nominal simulation, you can measure it back. So a standard linearity check, so that's shown here. injected top mass on the x-axis, measured on the y, and you see we get a very nice linearity. We add 70 MeV systematic for the possible non-closure here. Now, with these profile likelihood fits, you can worry that you've kind of over-relied on the Pauhay-Pittier simulation that you've used for the nominal simulation and lots of your systematics. So we did a test here where we took some alternate TT-bar samples that have not been used at all in the fit. So one of those is a Sherpa sample with different jets at next leading order, and then a Pauhay-Pittier sample with a change of one of the other settings in Pittier that we didn't include in the systematics model. In each case, we obviously add the nominal background, we need the background, and then we eject the combined sample into the fit as if it was data and see if we can extract back the mass. So of course we don't expect exactly zero bias here because these are slightly different models, but what we want to see is the bias is smaller than our modeling uncertainty. And indeed we see biases here less than 0.08 GeV. So we have some good evidence here that the fit can deal with a different model to the one we have in the fit, and of course the model in reality is not exactly Pauhay plus Pittier. So that gives us some good confidence in the simulation. So now we want to start looking at the data, and here we have a nice feature of the analysis that we can first fit these two distributions that are telling us about the systematics, so our W boson mass MJJ and our MTJ, which was telling us about the recoil parameter, because neither of these have top mass dependence. And because we set the fit up that we use only the mean of the top jet to give us the top mass sensitivity, when we add this to the fit, we add one data point, essentially, or one data value, and one extra free parameter for the top mass, so the nuisance parameters stay unchanged. So we could check all of our nuisance parameters and do the studies I'll show on the next slide without looking at the top mass in a fully blinded way, and then unblind and just look at the extracted top mass. Okay, so let's start to have a look at the fit to the data. So these are the two, I'm going to call them the auxiliary variables, so our reconstructed W boson mass on the left as you look, and the MTJ, so the observable sensitivity to recoil on the right. The top row is the pre-fit, bottom row is post-fit, and again, as before, the open shaded histogram is the TT-bar simulation, red is the background, and the black is the data. So when you perform the fit, of course, when you do a profile likelihood fit, you significantly reduce the systematic uncertainty, so you see the band shrinking here. Now, the data simulation was already quite good before, but then it improves, of course, afterwards. That's kind of guaranteed by the fit. And that is happening because you're moving around some of the nuisance parameters. So in this plot, we show you the most important nuisance parameters in the measurement. And for now, you can just look at the black points, and these tell you the fitted value of the nuisance parameter on the bottom axis, where 0 is nominal. So you see some of them are fitting a little bit away from 0, but in all cases within their error of 0. And you notice some of them are constrained. So example, the recoil parameter here, of course, because we've added this distribution, which is telling us about the recoil, and it agrees with the nominal, which you could kind of already guess from the pre-fit plot here. Other important certainties, of course, are jet energy scale, where we have sensitivity coming from the W mass distribution. Okay, so we've got this fit, but it has a goodness of fit when you do this, but it's maybe not quite enough to be convinced that you should definitely just apply this to the reconstructed top jet mass and extract the top mass. So we wanted to try to do a bit more checks first. So conceptually what we do here is we fit in the two auxiliary observables, and then we essentially extrapolate that model to our reconstructed top jet. And so we can kind of test that procedure by taking the same fit that's in our auxiliary variables and extrapolating it to other variables inside the TT-bar events. So using the constrained fit, so this fit with the constrained nuisance parameters. And we can see if the data agrees with the constrained model. So there's 3 examples of that here. So the first one is a lepton transverse momentum distribution, so kind of basic kinematics of your TT-bar event. Second one is the PT of the second leading jet inside our top jet. So there's 2 or 3 jets inside the top jet. And the third one is a variable where we look at a subset of events where there are 2 extra jets. So we're kind of here probing the region where the shower should be important. And we look at the delta phi between that jet and our top jet. So it's telling us something about the modeling of QCD radiation in the events. So you see in all cases that the systematic band here is rather small. That's because we're using our constrained model. But you see, in every case, the agreement between the data and simulation is good, and the lowest probability chi-squared we have here is 0.19, which is this middle distribution. So after this, we're kind of happy that the constrained fit we have is in a good place, and we can apply it to the observable we really care about, which is the mass of the top jet. So let's do that. So that's what we do, and we then, at this point, of course, get the top mass measurement, so 172.95 plus or minus 0.53, and that's the most precise Atlas top mass measurement from a single channel. This distribution you've seen already. This is the top jet mass distribution before the fit, and now this is the top jet mass distribution after the fit. So remember, in the actual fit, we only use the mean, but we've now projected the fit result onto the full distribution, so we can check the agreement is fine. So you'll notice the uncertainty is slightly smaller than expected. So it's 51 expected. We have slightly less events in the high PT regime in TT bar, which is a kind of known effect, so that's driving that. But the breakdown of uncertainties is very similar to what we expected from the simulation, so dominated by jets and TT bar modeling here in the top two contributions. But the statistical uncertainty is not zero here, so 0.27 GeV, so still room for the bigger data samples to help us out here. Another look at this plot. So we saw this plot earlier and looked at the black points. Now we want to look at the red and blue bars. So these tell you the uncertainty contribution of the individual nuisance parameters. So of course, many nuisance parameters in the fit, and we just show the top 15 or so here. So you see the picture here is that there's quite a number of uncertainties all contributing 0.1 to 0.15 GeV, and they're all, of course, components of the ones we saw in the table, so jet energy scale, and then things like to do with the TT bar modeling, so you see final state radiation, for example. Now, one thing you won't see if you spend some time looking at the plot is a nuisance parameter for the light to Quark-Gluon response difference, which I spent some time talking about 20 minutes ago or so. And this is because of the improved treatment that I showed you earlier. So the kind of closest analogy here is our run-1 lepton plus jets result. This was not boosted, so it's not a perfect analogy, where we had 0.22 GeV from this uncertainty, and now this is less than 0.1 here. And the nuisance parameters actually don't even appear on the plot because there's 3 of them on here. So that's a very nice improvement that's helped us with the precision here in this measurement. Okay, we also want to check the result is stable in the data. So we split up the reconstructed top jet mass in 3 different ways: by lepton flavor, by the dataset year, and how many jets are inside the top jet. So that's shown here. And each time we do a fit where there's 2 mass parameters, and of course they should always come out consistent, or we would have some evidence of something that's not in the model. And they do. There's quite a significant correlation here. That's why the error bars overlap here each time. The black line is just the nominal measurement. So all the pairs agree with the 1 standard deviation. So we have excellent stability within the data set. Okay, so now we can start to look at how this compares to all the other measurements. So this is this Atlas status now on the top quark mass from the direct measurements. So everything above the bold result there, the run-1 results, and then the bold one is the run-1 combination. So this is the new result, which I put the little arrow, and you see the precision here is almost as good as the whole run-1 combination. So a really nice step forward in precision, and excellent agreement, which you can see visually. The band here and the line show the new result. You see excellent agreement with our previous measurements. Here's the situation looking, so this is the same plot I showed earlier, but now putting the new result on. So we've got the Tevatron combination at the top, the run-1 LHC combination. This was an earlier Atlas result in 13 TV, so 3 more 13 TV results, including this precision CMS one. So you see we kind of sit in good agreement with the run-1 result and kind of between where the Tevatron and the precision CMS measurement are. So I think we've added some really important new information on the top quark mass with this new measurement. Okay, so I'm getting near the end, just about on time, sort of. So a little bit of an outlook. So I said earlier we have a non-negligible statistical uncertainty, so that's kind of promising for the future. And we know within Atlas that we hope we can improve our jet energy scale further. So there's 2 papers here that interest people should have a look at. And people, unless they were sleeping, will have noticed we're doing the European strategy process. And so we projected this result to higher luminosities. And we did 4 scenarios. So the first one, we basically assumed no improvement in our systematics, which is very pessimistic. And then 3 more scenarios where we assumed improving things kind of in order maybe of somehow how likely they might be. So the first one is improvements in the jet energy scale, kind of motivated by these publications. The second one is the TT-bar modeling, so that needs some theory improvements or use of our data. And the third one is further improvements on these flavor uncertainties that we already improved in this round. So if you do that, you get this plot. So this shows you, so this is the current expected result in the blue dot and how it evolves with luminosity. So high luminal LHC hopefully will get us to the right-hand edge here. And then the different colors of the different scenarios. And maybe just to point out 2 points. So if we get the kind of relatively conservative, I would say, improvements in the jet energy scale, we can get to 0.32. If we can kind of do all of this stuff, we can get below 250 MeV precision on the top mass with one analysis. Now, this projection is fairly simple, so it assumes we use exactly the same observables and binning as the common result. So for sure, this can be done better with clever PhD students and so on. And all of this, of course, it looks completely trivial when you make this plot, but it's a huge amount of work, experimental and theoretical, but I think it's an aim we should have in mind when we have the high luminal LHC coming in the next years. Okay, so that gets me to the end. So I presented a new measurement of the top quark mass, 172.95 plus or minus 0.53. A single most precise measurement from Atlas. And the precision is driven by this combination of the boosted selection, the improved treatment on the jet energy scale I discussed, and the fit technique we had. And the method should scale quite well to the high luminosity LHC. Probably a couple of minutes over.
Thank you very much. Congratulations to the results, and thank you for the very clear seminar. We have time for questions, and we start in the room. Yes.
Mark, thanks for the talk, and congratulations on the result. So for the, I was going to ask something that you said at the last page, actually, in your summary. So you do have, not the previous one. So you, not the previous one, sorry. Yeah, here. So you do have this improved jet energy scale from the single particle measurement, which can be even a factor of 2 in some cases. So can I understand that the number that you have in the next page is including this, is an expectation of this? And then what would it require for you to, and why you didn't use this improvement already in this result?
Yeah, so that's a good question. So what we did here for this first improvement here is we reduced the pile-up uncertainty really by an amount described in this first paper. Okay, so that was really like, it's quite a big factor. It's like a factor of 7. For the other parts of the in situ jets, we improved them by a factor of 2. So that's less precisely aligned with this because this hasn't yet gone into our particle flow jets. So I think maybe it remains to be completely seen what final precision we'll get. So there's a factor of 2. It's written, the note is now on the web. So there's a factor of 2 in all of the jet energy scale, apart from the pile-up where we took I think it's a factor of 7 that was in this paper. Answer that question. And then the second part of the question was, why didn't we put it into this measurement? Yeah, so Atlas did a reprocessing of its data a couple of years ago, and the sort of strategy was that some of these later developments, so you see these papers are in the last couple of years, will go into that reprocessing. So that data, that is a consistent processing of both the run 2 and the run 3 data. So we should also be able to deal with, for example, the correlations across those data sets. That, of course, is going to take some time to see actual top, particularly things like the top mass, where, as you see here, it takes some time to get to this.
From the outside, please use the raise hand feature. We have another question here.
Thank you so much for this really nice talk. So I had a question to slide 14. So you were saying that there's significant rejection of pile-up jets using the particle flow algorithm. However, what I don't understand, so it seems like at high eta you have like a factor 10 more fake jets than in the central region. So I was wondering how you deal with this situation and why you have so many of them.
Yeah, that's an excellent question. So the one thing to mention here is, of course, so in this, I probably didn't put the eta selection. So when we did a top mass analysis, we're interested in jets inside the tracking volume. So for this analysis, the impact of those jets is very small. It would only come through the missing transverse momentum. So you might think that the green and the red line or the blue line should all overlap here because essentially the particle flow jets become calorimeter jets in the forward region. But here we have a slightly different definition of the jets. So the red and the blue line are using our local hadron calibration on a cluster level before we build the jets. The particle flow jets use a correction to the EM scale. And so this means they can be slightly different. In the paper, I read the paper, I didn't write this paper, we wrote that these are equivalent performance. I'm not quite so convinced, but there's people who know a little bit better than me in the audience. There is a different definition in the calorimeter, which is I think, what's driving the difference.
Okay, thank you so much.
Hi. Can you comment in view of a possible combination with the other top measurements, what kind of correlated systematics you have with them? Because I would assume
so
a large fraction of them are correlated, right?
That is an excellent question. So, no, I'm going to go back actually. So we have some experience of this now. So we rather recently, that's not going to work. So when we did this combination, so we combined all of the run-1 measurements between Atlas and CMS. And so all these measurements have common uncertainties that are correlated. What we saw is that many of the measurements have rather different sensitivities to different uncertainties. So that means often the overall correlation between pairs of measurements is not so large. So if you look here, there are significant gains when you do the combination within an experiment, but also cross-experiment. So you see, despite both these combinations here, Atlas and CMS, the systematics dominated, the combined uncertainty is actually more like what you would get from uncorrelated. So the total correlation is rather weak here. Now, I think one thing that is going to be a challenge for us is combining the 13 TV data with the run-1 data. Particularly on the TT-bar modeling side, we've changed quite a bit of the generator setup. And so we need to look rather carefully at whether we can understand the correlations well enough to do that combination. That is not done yet, I think. I think the 13 TV, once we have those analyzed in all the same kind of release and things, will be kind of attackable. I think combinations with run-1 is, well, it's something we should look at, I think.
Yeah, hi, Mark. Thanks for the very clear talk and a beautiful result. It's congratulations with that. You made quite a lot of very different choices in this analysis compared to the CMS boosted analysis. I think it would be very interesting, maybe at the next LHC top working group meeting, to have the two analyses next to each other and see all the differences. I think one difference is that in the end, the CMS analysis has a dedicated, let's say, flavor uncertainty for the mass, the jet mass scale. So basically, in addition to using the W jets to fit the jet mass scale for light quark subjets, there is an additional variable introduced to then add the B subjet, but not assume that everything is proportional with each other. Did I understand correctly that you don't have that?
So we have we have 3 uncertainties in the new flavor treatment for the energy scale of the B jets, which are completely uncorrelated from the energy scale of the Ws, of the light jets. And so they are not constrained in the fit. So those uncertainty contributions are basically the same whether we do the 1D or the one-dimensional fit or the full fit at the end.
But those are, let's say, the standard B-jet variations that you also use for low PT jets, right? So what worries me is that we have 35 uncertainties on the jet energy scale, but this is to fix the PT. We never studied in so much detail the jet mass.
Okay, so the question is
so that is the point. So there is no uncertainty for the B jet mass scale.
Yeah, so that's probably true to say. So when we do all of our jet energy scale variations, we do change the mass. So if you look at the way the calibration works, changes the PT, we keep the other things fixed, so the mass is also shifting. So it's not true.
But the assumption is that the mass shifts with the same factor as the PT.
Yeah, similar. Yeah. So that the B jets.
Sorry, similar or the same?
So if you shift
up
it's the same nuisance parameter. It's the same. So we have 3 nuisance parameters for the energy scale of the jets that will change both the energy and the mass in a correlated way.
With exactly the same factor.
Yes, but because it goes through the full momentum conservation, right? So it doesn't. Yeah. Now the mass of the B jets is not particularly important here, right? So in the invariant mass of the top is driven by the fact that you've got either 2 or 3 subjets, and the invariant mass is driven by the energy scale of those jets and the fact they're at an angle to each other. It's not driven by the B jet energy scale, or the B jet mass.
Yes.
Or maybe
although the B jet mass is part of the mass of the jets, right? But I'm more concerned that in a fat jet, you might have overlap effects between the subjets, and things change, and then there also the B jet mass would have an effect.
Yeah, so Atlas, we've done previous studies where we've looked at whether the jet energy scale changes when we have close-by jets. We don't see any effects like that. I mean, the analysis, we also checked the data Monte Carlo agreement of the mass of the reconstructed small R jets, and we don't see, within the uncertainties we have, we don't see any problem with the data Monte Carlo agreement radius jets.
Pardon, I had some impression that there's a misunderstanding. Are you talking about the jet mass? Or what mass are you talking about? So you're missing uncertainty on the jet mass, on the small r jet mass, or did I misunderstand?
Yeah, so your observable in the end is the jet mass of the fat jet, right?
We only use small r jets here.
The observable is indeed a fat jet mass, but the fat jets, I don't want to call them the fat jets, the large radius jets are made of individual 0.4 jets, of which there is always at least 2. So the invariant mass of that jet is largely driven by the energy scale of the jets, not by the mass of the small radius jets.
But for example, if you have, you need 3 subjets to fit the W with the 2 light jets. Is the assumption that for jets, for events where you only have 2 subjets, you have the same correction factor as for events where you have the 3 subjets?
I mean, there's no single correction factor, right? So there's 35 nuisance parameters, and they affect the jets differently, right? So it's not quite right to say there's one single correction factor. There's no dedicated uncertainty on the mass scale of the small radius jets, but that's a very small effect, so we checked in the simulation. And if we had a problem in the mass scale, so when we do this check near the end, so here we split up, sorry. So here we split the sample into events where there's just 2 jets inside the large radius jet. So we must then have 1 jet that's, if you like, got non-zero mass, not just QCD mass, because it's likely this has got the W inside 1 jet. And we've got the set where there's at least 3. So then we fit the mass separately, and they agree. So if we had a significant data Monte Carlo problem, it would show up here.
Okay. I invite you to also chat after the seminar for more details. Is there a last question here? Not outside, so let's thank Mark again